Okay, so what we're going to do is continue here with chapter 7, energy. And now we're looking at the third part of this, which is going to be about work and energy. Okay, so we can tell this part 3. All right, so let's go look at energy again. Sometimes energy is called the ability to do work. So an object or system that possesses energy has the ability to do work. So it could have electrical energy. It could have heat, like your automobile engine has heat because it's burning gases. Those gases push on the cylinder, and that provides the force to make your engine go in a combustion engine. And so anyway, the energy is there, and that energy can do work. And energy can be done by a system, and the amount of energy in the system decreases. So if you've got a battery that has stored electrical energy, and then you use it in a flashlight, well, then it has done what has used up some energy, and so the amount of energy in the battery decreased. And so another type of system might be, you might think about your automobile again. It does work, and so the gasoline has been turned into force, and you're pushing, maybe you're pulling a trailer, and it does work on that trailer, and so the amount of energy that's available in the system decreases. But when you do work on a system, it gains energy. So you're pushing a cart in a store, and you're pushing on the cart, and it gains kinetic energy. So your system, the body, has lost energy, but the system that's the cart has gained energy. So both things can be going on at the same time. Energy has to come from somewhere, some system, and then it goes to somewhere. Now, when we do work, we transfer energy from one object to another. Okay, so we saw this slide before, and now we're going to examine it a little more. So work can change the amount of energy in an object. Positive work adds energy. And when you have positive work, that's when the force and the distance are in the same direction. So you're pushing on that lawnmower, and so you are doing work, and you're adding energy to the lawnmower. A car engine speeds a car up. But negative work is when the force and the distance are in opposite directions. So you've got a hockey puck sliding across the ice, but friction will eventually slow it down. And friction is always a force that's opposing the motion. So it's in the opposite direction. Right? So your hockey puck is sliding. The motion, the velocity, and the distance are in one direction, but the frictional force is in the other direction. Okay, so that case, you are taking energy out of the system that is the hockey puck, and that heat is heating up the floor of the ice rink. Okay, so here's that cyclist again. She was rolling along at 5 meters per second. And so to come to a stop, she applies a braking force on the bike. Oh no, what happened to the other slide? Okay, so she applies the braking force of 50 newtons. What distance will she travel till she comes to a stop? So remember that the kinetic energy that we gave her was 1,000 joules. So her energy that we did before, going kinetic energy, 1/2 mv squared, right? And what's happening is that she is, that came out to 1,000, so 1/2 of 80 times the velocity, and the velocity was 5 meters per second. Okay, and that came out to 1,000. So she had 1,000 joules of energy. That's her initial energy. Her final energy is going to be 0. Kinetic energy is going to be 0 because she's going to come to a stop. So her final energy is going to be 0. Her initial energy must be 1,000 joules. And so how much must the work be? Well, in this case, she's coming to a stop. So the force, the braking force, is in the opposite direction. So we're going to give this a minus sign, right? That will make this work out. The minus sign would be the 1,000 joules of work that you need to do to make her come to a stop. Okay, so the work that needs to get done is equal to minus 1,000 joules. And that equals force times distance. Well, how much force is she using? 50 newtons. And the 50 newtons actually is in the negative direction, right? Because she's applying a negative force. And then that's going to be times the distance. So we can find out the distance, divide the negative 50 into the 1,000. And so we would end up with 20 meters, right? Okay, so she travels for 20 meters before she comes to a stop. You always have to give yourself plenty of room to come to a stop on a bike. Okay, now what if she was going to speed up? So she's at 5 meters per second, and so she could speed up by applying a force, of course, in the same direction. Okay, now what is the work energy theorem? The work is done, and kinetic energy is changed or transferred, right? And the work energy theorem is that the net work that's done equals the change in the kinetic energy. So that is just what we were looking at a minute ago. There was net work done that created a change in the kinetic energy. Okay, and the net work is the net force times the distance. Okay, so we've got our baseball player here, and he's throwing this ball. And so let's find out how much energy he puts into making this ball go. Okay, so he's the pitcher. And so when he starts with the ball, it's going 0, right? He's holding it. It's 0 meters per second. And then he reaches his arm way back here. And then he goes forward with his arm. And let's say that he covers a distance of 2 meters. Okay, so what we're going to figure out is how much force this baseball player actually uses to change the kinetic energy of the ball. So let's go do the math here. And let's say the ball, once he's pitched it, he's a good one. So let's say it's going 50 meters per second. The change in the kinetic energy is the kinetic energy final, minus the kinetic energy initial. Now, this ball didn't start out with any kinetic energy, so we can make that into 0. And we just need to find then the work, the net work, which would be the net force times the distance is going to equal the change in the kinetic energy there. So in this case, it's just the kinetic energy final. And so that's going to be 1/2 mv squared. So this is the formula that we need to solve. We want to solve it so that we find the force, because we've got the distance and we've got the velocity, and all baseballs are around 0.2 kilograms, so we've got a mass. So we're going to figure this out. Okay, so 1/2 0.2 kilograms. The velocity is very fast, 50 meters per second squared, so that's like 100 miles per hour. And so that's going to give us 50 squared. Well, 0.2 over 2 is just 0.1. That's one reason I like 0.2 for a mass. And we've got 50 squared, and 50 squared is going to be 2,500. Half of 0.2 is 0.1. So altogether, we would just end up with 250. Okay, so now we've got 250 is equal to the force times the distance. The force is what we want to find. The distance we already know is 2 meters. That's how far he reached his arm back and then stretched it forward. Okay, so now we can solve for our force. And our force is going to be 250 divided by 2, which is 125. So now we know that the net force is equal to 125 newtons. That's how much force this baseball player has to use to throw that ball. So that's a pretty good force for someone to expend on that little ball. Okay, so anyway, so when we talked earlier about the coming to a stop, one thing is that it takes a lot of energy to bring something to a stop. You have to get rid of all the energy that a car has. So one thing is that a car that is going here at 32 kilometers per hour, so that's about 20 meters per second. Yeah, that's about 20 miles per hour. Let's see. Versus one at 64 kilometers per hour. So the speed is doubled, which means the energy is 4 times as much. So what happens is that the stopping distance for this car is only 8 meters for the blue car. But because you have to use the brakes to bring the car to a stop, then you have to get rid of all that energy. Then you actually have 4 times as much energy for the red car. And so the braking distance is actually 4 times larger, 32 meters, as opposed to 8 meters. So, right? Twice as velocity, 4 times as much energy. Okay, and so that is one reason in city streets and stuff, they're often labeled with velocities that you think are way too small, like the road looks wide. You can go at 20 miles per hour or faster, right? Maybe they're labeled 20, but maybe you go 30 or even 40. The reason they're labeled 20 is because in neighborhoods, there are always cars pulling out, dogs running across the street, kids throwing balls. So you never know what's going to happen. You have to be ready to stop. And so what happens is that you want to be ready to stop in a short distance. So you've got to be going at the slower speed. You just can't stop in the same distance if you're going at a faster speed. Okay. So let's just do a little bit about power. Power is the rate we use energy or do work. So it's the rate, meaning it's per unit time. So power is work divided by time, or energy divided by time. And power has units of joules per second. which are watts. So that's one unit we actually use in America, are watts. And that means joules per second. So if you've got a 100-watt bulb, it's using 100 joules of energy per second. And this introduces another W, because watts, the unit, is listed as a W too. So we've got way too many W's. We've got W for work, we've got W for weight, and we have a W for watts. So be careful, don't confuse work and watts with weight. Okay, so force has the unit, the Newton. Work is the joule. Energy is a joule. But power is a watt. It's a joule per second. Okay, and here in America, of course, we use the horsepower, which is foot-pounds per second. That's one way to do it too. 1 horsepower is 550 foot-pounds per second. That's about 746 watts. Okay, so here's a problem. We've got this bike that stalls out. Somebody pushes it 10 meters along the road in 20 seconds, and you have to use a force of 150 newtons. Let's calculate the power. So power can be work. Work can be force times distance. So here we've got power is work divided by time, but we can write that as force times distance over time. And so our force is 150 newtons. Our distance is 10 meters. Our time is 20 seconds. So put those all together, and it comes out to be only 75 watts, which isn't a lot. Okay, so power is pretty easy to calculate. We'll see different versions of power in the future. Now, sometimes when we do it for electricity, we'll talk about energy more, because you don't really see a light bulb doing work. Okay, now you can also turn this formula around so that you get energy is going to be power times time, or work time. So energy or work equals power times time. So here's a 100-watt light bulb. Shine it for 2 minutes. How much energy did you use? Well, the power is the 100 watts. The time, of course, you want to do in seconds usually. So 2 minutes is 120 seconds. Put those together, and you would get 12,000 joules of energy. Okay, so that's the end of this part. The next part will be simple machines. Do that another day. Okay, so going to stop this section.